Wonderful. Okay. Hello, everyone, and welcome to this seminar. Today, my name is Becky Peterson. I'm faculty in electrical and computer engineering at the University of Michigan in Ann Arbor, Michigan. I'd like to welcome you to our seminar today. This seminar is part of the IEEE Southeast Michigan chapter. We're a joint chapter of the Electron Device Society, Microwave Theory and Technique Society, Antenna Propagation Society, and the Photonics Society. And so with all of those different chapters, we really cover all of the bases of hardware in electrical and computer engineering. And we like to offer a variety of seminars that speak to those technical topics of interest to our members. And so today I'm really delighted to welcome Dr. Jordan Budhu to our seminar. He received his master's in electrical engineering from Cal State University in Northridge, and then a PhD in electrical engineering from the University of California in Los Angeles in 2018. He then came to University of Michigan, and he is now a postdoctoral research fellow and a lecturer in the Department of Electrical and Computer Engineering here at University of Michigan. He's won many different awards, including fellowships and technical awards, teaching awards. He's quite well recognized in his field, and he's going to talk to us today about his work in next generation metasurfaces, a multiband passive metasurface for arbitrary amplitude and phase control. While he's speaking, I have kept all of you muted. You can also mute your videos if that helps avoid distraction for the speaker and everyone else. And then you can post your chats in the chat throughout the talk, and I will read out anything that is urgent to Jordan, and anything else we will leave to the end. And then you'll be able to unmute and ask your question, or I will read any questions that are remaining in the Q&A. So please feel free to use the chat to post your technical questions. And with that, I'd like to welcome Jordan Budhu to speak.
Thank you, Becky. Yes, so here I'm today going to present to you some work that I'm doing on next generation metasurfaces, multiband passive metasurfaces with arbitrary amplitude and phase control. And we'll define metasurface, and we'll define what we mean by amplitude and phase control so that you can follow along. So I'm Dr. Jordan Budhu. I'm a research fellow and a lecturer in the radiation lab at the Department of Electrical and Computer Engineering at the University of Michigan. So the outline of the talk that we're going to present is there's about 4 categories, and they all evolve in our understanding and our applicability to the final goal. The first one is single layer passive metasurface reflectors. We'll talk about that. That was the first work that we did. And then we evolved into dual layer passive metasurfaces for dual band operation. So we were able to add some degrees of freedom to get dual band operation out of it. And then we went to a single layer passive metasurface or arbitrary beamforming. And you understand how that sequence of ideas evolved. And then finally, we'll talk about 3D passive conformal metasurfaces, which is our new work. And we'll conclude after that. So how can we beamform? In order to beamform, we have to be able to control the amplitude and phase of radiation at discrete points in the aperture. There are 4 main ideas I thought of that might highlight the different ways to do that. And one is phased array antennas. So in the upper left, you see a phased array antenna. And the difficulty with phased array antennas are that it requires attenuators or amplitude control and phase shifters on the back of the substrate. So it's a multi-layer PCB, and you might have some ICs on the back, and you have your radiating elements on the top, and you'll have to connect those through vias, and you'll have some ICs in the back that will control the amplitude and phase. Or you could shape a reflector. You can shape a reflector to get amplitude and phase control, but there you have limited control of the amplitude. Another way is waveguide slot arrays. You can position your slots to get some level of amplitude and phase control, but there you would have difficulty doing arbitrary beamforming at dual bands. And then finally, you could have multi-layer metasurfaces, and you can do amplitude and phase control if you add multiple layers to get additional degrees of freedom. But the problem there is it consists of multiple layers. So we're going to try to find a way to do arbitrary beamforming in a simple way with a single pattern metallic cladding over a grounded dielectric substrate. And that'll be the main goal of this presentation. So what is metasurfaces, and how do we utilize these simplification of the complex geometry in order to design metasurfaces? So if you look in the upper left here, we have a atomic picture. We have a metasurface with patterned elements, and as the frequency of operation becomes lower and lower, then those elements become smaller and smaller in terms of wavelength, and what you see really is an averaged picture, an average response from all the elements. So we can model that average response as a single element that has a homogeneous sheet impedance. We call that eta S here. And that is the sheet impedance that we can assign to the entire panel of these patterned elements. As long as those elements are small in terms of wavelength, then they scatter in an average way. We only see the average of the scattered fields. So the key about that, the key to that is that the pattern surface and the homogenized sheet, they share the same S parameters. So what do those S parameters look like? How do you go back and forth from the sheet parameters and the S parameters themselves? Well, in general, if you have a bi-anisotropic sheet boundary, it can support both electric and magnetic currents, and both the electric and magnetic field can excite electric and magnetic currents. That's described by this matrix equation up here, this boundary condition in general. So to get to S parameters from your sheet parameters, which are the admittance, the electrical admittance, you have the magnetoelectric and the electromagnetic coupling terms, and you have the magnetic impedance. From those terms to the S parameters, you use this equation here. And if you need to go to the material parameters from the S parameters, you can use this sort of equation down here. These equations are for the general case of infinite homogeneous bi-anisotropic sheet boundaries, which are assumed to be infinitely thin. In this work, what we're going to do is specialize to the case of a finite inhomogeneous surface, and we're also going to further specialize it to ones that support electric currents only, and therefore can be described by a single parameter, which is this admittance matrix. And the inverse of that admittance matrix, we're going to call the electric impedance. And furthermore, we will model the actual thickness of the metasurface itself. So how do we do that? If we're only supporting electric currents, then our boundary condition here collapses into a single equation, the impedance boundary condition. We're only supporting electric currents, and we only have electric fields that excite those electric currents. Therefore, we can describe the metasurface through a single parameter called the admittance matrix, or the impedance matrix if we take the inverse of it. So our metasurfaces in the beginning of the work will be two-dimensional in the sense that they do not vary in and out of the page. So this metasurface here is a patterned metallic cladding over a single dielectric spacer and a grounded dielectric, or sorry, the ground plane underneath. That geometry does not vary in and out of the page. So we're going to do exactly what we had just mentioned. We're going to take each of these elements, these patterned claddings elements, and we're going to homogenize them and assign to them a single impedance, which is representative of the average response that element would provide. And that is called homogenization. So once we have a homogenized sheet, which is basically an array of homogeneous impedance sheets, then once we have that sheet, we can use this boundary condition here to describe its response to an electric field given, or the occurrence that are excited by a given electric field through its impedance. So how are we going to design it given this boundary condition? Well, we're going to construct an integral equation around this boundary condition. So if we split the total field into incident and scattered, then we can write just the following equations. So we can stipulate the desired scattered electric field. Typically, we know the incident field because we're going to excite the surface that we're trying to engineer the response of, and the scattered field is what we want to provide or produce. So we can specify the scattered field and stipulate it. If we stipulate the scattered field and we know the incident field, then we know the total field. That means we know the left-hand side. Step 2, we're going to express the scattered field in terms of surface currents through an integral equation. So we're going to construct, or we're going to express the scattered field rather, in terms of the integral equation shown here, which is the convolution of the Green's function with the current density. Step 3, we're going to solve for those currents which satisfy the equality using the method of moments paradigm. So we'll expand the unknown current density in terms of known basis functions underneath the integral sign, and we'll recast this integral equation into a matrix equation, solve that matrix equation, and obtain the unknown currents. And step 4, we'll return to this impedance boundary condition once we know the currents and we know the desired total field that we stipulated the scattered field component of, and we can solve for the sheet impedance that's required to achieve the transformation that's desired. So we'll outline the 4 steps in the following slides. So step 1, we said we have to determine the desired total field. As I was alluding to, we know the incident field, its magnitude and phase, if we write it in polar form. And we stipulate the scattered field phase. We want to collimate the beam, let's say. But we don't know the amplitude. And the way we can find the amplitude is we can attempt to satisfy local power density conservation at the surface. So what we do is we set the incident power density equal to the negative of the scattered power density locally at each point along the surface. And what we're trying to do there is say that the power that comes into the metasurface locally at each point is therefore reflected. And the hopes is that we would get a passive metasurface in doing that. So that's how we come up with the amplitude. We satisfy local power density conservation at each point along the metasurface, and we can derive a formula to give us the unknown amplitude. So we stipulate the phase, we derive the amplitude based on conservation of power, and then we have our desired total field, which is one key step in designing metasurfaces. In step 2, we formulate the integral equation. So now we know the left-hand side, and we're going to formulate an integral equation around it. So we split the total field into incident and scattered, and then we throw the scattered field term to the right-hand side, and we construct an integral equation out of that. We express the scattered field in terms of an integral of the Green's function and the current density. So what I have here is a two-dimensional metasurface invariant in and out of the board. We have two layers. One is the metasurface, the actual pattern layer, and then we have a layer 2, which is a ground plane layer. Perfect electrically conducting, we know its impedance and total field as 0 and 0. So for observations made on layer 1, we can construct an integral equation using this boundary condition as the incident field is the total field, the right-hand side, plus this, or it's actually minus, but we absorb the minus sign into this coefficient, which is the scattered field due to the currents on the metasurface itself, and then plus the scattered field due to the currents on the ground plane itself. So this is for observations made on the metasurface itself. For layer 2, we do the exact same thing. We have the incident field on layer 2, but we know the total field down there has to be 0 based on the boundary condition for PEC. We have the currents due to the metasurface and the currents due to the ground plane and the scattered fields associated with those. So now we have two integral equations that we're going to couple and solve simultaneously. So the way we do that is we expand the unknown currents under the integrand in terms of known basis functions with unknown complex coefficients. And by using point matching at the center of each of these elements, which are, the currents are expanded in terms of pulse basis, and using point matching, we can transform the two integral equations into a matrix form, which is solvable on a computer. So this is the exact same equation. We have the incident field. The upper row represents the first integral equation for observations made on the metasurface. We have the incident field. We have the impedance matrix, or the scattered field, which is this impedance matrix multiplied by its current coefficients. Plus, we have the total field, which consists of the impedance of the metasurface multiplied by the currents on the metasurface. And then we have the scattered field due to the currents on the ground plane as the impedance matrix multiplied by the currents on the ground plane. And then we have the second integral equation, which is for the ground plane. We have the incident field on the ground plane. We have the coupling matrix of the ground plane to the currents on the metasurface, and the coupling matrix from the ground plane to the currents on the ground plane. And then we have this 0 matrix here because we know the impedance of the ground plane is 0. So using the boundary condition, so this is our boundary condition, right? The total field is equal to the sheet impedance multiplied by the current. If we write that in sort of discrete form, which is based on sampling the desired total field, then we can replace this eta sheet times this current over here with the following matrix. So we move that total field, the known desired total field, to the left-hand side. So then we have the incident minus the total field, and then we have all known quantities in here, unknown currents that we're solving for, and everything is known and solvable. So the way we solve for that is we invert the impedance matrix and multiply both sides by it, and we can solve for the currents. Once we have the currents, then we can find the sheet impedance required to do the transformation by dividing the desired total field by those solved currents. So you get something like this. And what this shows is you have a real part and an imaginary part. These sheet impedances are complex valued. And what you'll notice if you zoom into here is that the real part of that complex sheet impedance has sort of equal negative and positive contributions. And this is undesirable because we can pattern metallic surfaces and achieve reactances, but it's much more difficult to achieve losses or gain with patterned surfaces. We'd have to make the surface active. So generally, we want to get rid of this real part. And that's one of the biggest difficulties with metasurface design. So one key point here, though, is we did not assume local periodicity anywhere in the design phase, which is sometimes common in like reflect ray designs and things. We did the full coupling matrix between all the elements. So for example, if we have a 20 lambda wide metasurface, which is separated from the ground plane by lambda by 10, and we feed it with a point source, or not a point source, but a line source in and out of the page, which is 10 lambda up, at 1 gigahertz, we get the following results. So we have the incident field, which is a cylindrical wave coming from the line source, and we want that cylindrical wave to transform to a perfect plane wave. So we design this metasurface, which will have this sheet impedance shown in this figure. If we pattern this metasurface such that it can exhibit this complex sheet impedance, then we would get exactly the scattered field phase of a plane wave. We get a scattered plane wave, and that's the idea. But the problem is that that sheet impedance required is complex. So we have to find a way to, well, first we have to understand why it's complex. Where did the real part come from? So we revisit step one to determine the desired total field. In that step, we said that the total field is the incident plus the scattered, and we knew the incident field by knowing what source we're using, and we stipulated the scattered field phase, and we didn't know the scattered field amplitude. We tried to do conservation of local power density at each point on the surface in order to find this amplitude. If we expand the power density along the surface, then we can calculate that as 1/2 real part of E cross H conjugate, and we know that both fields exist on the metasurface simultaneously, the incident and the scattered field. If you expand this cross product here, then you will get three terms. You'll get the power density associated with the incident field, you'll get the power density associated with the scattered field, and you'll get this other term with the cross products, the mixing terms, which is due to the interference of the incident and the scattered field. So you have E incident cross H scattered conjugate and E scattered cross H incident conjugate. So what does that look like? So we know by design, we said that the incident power density is equal to the negative of the scattered power density, so that both these cancel by design. That's how we found the amplitude. We found this amplitude such that it generates a scattered power density equal to the negative of the incident. So these two cancel by design. This term is left over. And the whole idea is to set this equal to 0 so that we get a passive metasurface. If you look at this plot here, I have the incident power density in blue, the scattered power density in red. These two are exactly negative of each other, indicated by this black curve, which is the subtraction of the two. The green curve is the interference term. One thing you notice about the green curve is if you integrate that thing, you'll find globally, the power globally along the surface integrates to 0. So it's equal amount of power going into the surface as there is coming out of the surface. But this term here causes the problem. It leads to a real part of the sheet impedance because of the existence of there being power density, positive power density on the points of the metasurface and also negative at different points. So thus setting S incident equal to negative SY scattered led to global power conservation because this integrates to 0, but not local. What we could do is we could take some of this power, find a way to shuttle the power from points where there's positive power needed to points where there is negative power needed using surface waves. And that's what we'll do. That's the main theme of our solution. These designs are therefore called non-local power conservation designs. So let's see what the effect of this interference term, this power density interference term and the power density has on the sheet impedances that you obtain. So here what I've shown is the sheet impedance that we derived. And if we zoom in to the y-axis, then we can see how that the real part, the red curve, has equal positive and negative contributions. If we then superimpose that over the power density, then we see where points of negative power density, indicating we need active devices to synthesize that negative power, we have negative resistances, and that is indicative of the necessity for gain. When we have positive power density, we need to absorb the power, and that means we need positive resistances. So you can see they line up pretty well. So what is our strategy? What are we going to do to obtain purely reactive metasurfaces and get rid of this real part? Well, we're going to use gradient descent optimization, and we're going to try to obtain a purely reactive metasurface, which is consistent of only reactances, that will give us the desired transformation and therefore will not need any lossy or active surfaces. So the main idea is to throw out the real part of the sheet impedances and search for a reactive sheet, which gives the same near fields as the complex sheet. How is this going to work? What is the main idea? Well, the main idea is to engineer a certain number of surface waves that we add to the desired scattered field and the known incident field such that the total field at each point along the surface satisfies local power density conservation. These additional surface waves that we're going to engineer the surface to support, and we'll be excited, are not going to contribute to the scattered field because they are evanescent. So we're going to look for a surface. We're going to look for the sheet impedance that describes a surface, a reactive surface, that generates the correct number of surface waves, such that when we add them to the desired scattered field that we want to achieve upon reflection, and the known incident field, that total field is satisfies local power density conservation. So we're adding another field, and that additional field will not radiate to the far field because it's evanescent, and that additional field will allow us to achieve the passivity. So the way we're going to do that is we're going to throw out the real part, keep only the reactances. That seeds our optimizer. So we're at some point in the solution space that is seeded by the complex sheet, but without the real parts. Then we're going to use gradient descent with the cost function built around the near fields at 1 lambda away. So we want to look a little bit away from the metasurface to allow the evanescent fields to decay and obtain the same amplitude and phase in the aperture 1 lambda away as the complex sheet generated, but with our reactive sheet. So the cost function is the RMS difference between the scattered near field amplitude and phase from the complex sheet and that of the reactive sheet that we're trying to find. Okay, so the optimization results are shown here. We have the original complex valued sheet as the black curve. We have the reactive sheet. So what does reactive mean? That means I just threw out the real part and immediately solved for the response of the reactive sheet when I just threw out the real part of the complex sheet without optimizing it. So we can see what happens when we remove the real part. We get the red curve, which is a different near field. So this is a near field amplitude at a plane 1 lambda above the metasurface and the near field phase. Then we optimize that reactive sheet in order to make the near fields equal. And you'll see the blue curve. So the blue and the black curve agree pretty well, meaning that we were able to find a reactive sheet, which gave us the same scattered near fields as the complex sheet. And what we have here is what happened to the impedances. So remember, we started with this complex sheet, which had both real and imaginary parts. And we found an optimized reactive sheet, excuse me, an optimized reactive sheet, which is purely imaginary. The real part is 0. But our reactances now have become perturbed in such a way that we've excited those surface waves that will bounce back and forth between the open ends of the metasurface and give us that additional field that we need at each point, such that we can get passive metasurfaces. And we'll see that the patterns of the optimized reactive sheet agree well with the original complex sheet. Okay. So let's see what the surface waves look like. So what I'm doing here is I'm plotting the complex sheet's total field amplitude spectrum. So I'm taking the plane or the Fourier transform, obtaining the plane wave spectrum of the electric field, the total electric field, and plotting its amplitude along the metasurface plane right here at lambda by 10 above the ground plane. So the red indicates that I'm plotting the total field spectrum right on the metasurface. And what we see is, and I'm plotting the spectrum for both the complex and the optimized reactive sheet. So the complex sheet has very little evanescent content, which means it doesn't excite too many surface waves, or if any at all. And the optimized reactive sheet, it has a lot more evanescent content, meaning that a number of surface waves were excited. And it's those surface waves that allow us to achieve passivity. If I then look at the same total field amplitude spectrum at the 1 lambda plane, which is above the metasurface in the aperture, we see that the two spectra are exactly identical, which is exactly what we'd expect. We looked at the 1 lambda plane above the metasurface and built our cost function up there because we didn't want to observe these evanescent contents, right? Because these two spectra are not equal and the cost function would have never gone to 0. But by looking at this plane up here, these two spectra are equal and we can get the cost function to go to 0 while allowing these evanescent surface waves to develop. So we wanted to realize this. So we then came up with a library of pattern geometry that we could use to realize the reactances that we optimized. And we have an interdigitated capacitor, we have a meander line inductor, a gap capacitor, and a sort of a transmission line inductor, or a straight line inductor, which are the classic parts to use for reactive elements. We then patterned this metasurface using this optimized reactive sheet. We place it in between two parallel plates in order to make emulate an infinite structure in the vertical direction and a two-dimensional problem. And we simulated that in COMSOL using full wave simulation. And we got very good patterns. So the patterning of this optimized reactive sheet can be realized by using these types of geometries. And then we can realize these optimized reactive sheets. So then we wanted to see if we can push this idea and get dual band operation. And the way to get dual band operation, we have to add some degrees of freedom. So what we're going to present to you next is multi-layer metasurfaces for dual band operation. So I'm adding another metasurface. We have the pattern geometry or pattern metallic cladding over a grounded dielectric, and then we have another pattern metallic cladding over a dielectric spacer. So there are 5 layers in total: two metasurfaces, 2 dielectric spacers, and 1 ground plane. and we'll get dual band operation out of this. So to understand how that works, we look at the following figure. So the total field is still incident plus scattered, but now we're going to look at two different frequencies. And we find we stipulate the phase again, and we find the amplitude using local power density conservation, or matching the local power density again. So in the previous example, we had a metasurface over a ground plane. And the ground plane has a known total field and a known impedance, both 0. And the metasurface, the total field and the impedance of the metasurface are linked by the boundary condition that we're using to do the design. So the idea is this. What if we make layer 2, instead of a ground plane, we make it a metasurface? So now we have two metasurfaces. And the same situation for the top layer, but the bottom layer now has a total field and an impedance which are unknown. They are linked by the same boundary condition, but we can't specify the total field on the bottom layer, because we can only specify the total field on the upper layer because we want the desired patterns, the desired reflection characteristic, or the desired radiation is due to the currents on this surface. It's due to the currents on both surfaces, but the aperture is, the radiation is going out this way basically. So we can specify the total field that we desire here, which will give us the pattern. Down here, this contributes, but only in totality. Okay, so that's the idea. We're going to make the bottom layer a metasurface, but we have the problem of we need to solve for this total field down here. So the way we do that is the following. So if we go back, let me see here. If we go back, what we did before is we had the situation of a ground plane and a metasurface, and we constructed these two integral equations around them. We had the we had the total field here, which had the sheet impedance of the metasurface, and we had the known total field on the bottom layer, the ground plane, as 0, because it was PEC. And we constructed this integral equation, or this matrix equation, out of that right here. So remember this matrix equation, because it's going to be very similar. But instead of having 0 field here, we're going to have a contribution. So if we go back, we have this same matrix equation here. We have the total field appearing on the left of on the upper surface, but instead of having the total field of 0, we now have a sheet impedance, an unknown sheet impedance of that bottom layer multiplied by the current density. So this causes a problem because we don't know the sheet impedance, and we don't know the total field that we could have thrown to the other side. And additionally, we have this same matrix at both frequencies. So you'll see a superscript up here of F1 means frequency 1, and a superscript up here of F2 for frequency 2. So we have to solve both these matrix equations simultaneously. And we came up with a pretty clever way to do that, and after some thinking about it, and I'll try to walk you through our approach here. So we make an initial guess of eta 2. We make the initial guess of 0. So if I guess this to be 0 at first, then I know all of the elements of this matrix and I can solve for these currents. So we make an initial guess of 0. Then we solve for the currents by inverting the matrix, same as we did before. Once this is known, we can use the same approach as before. Then we obtain the sheet impedance, same as we did before. Once we know the currents and we know the desired total field in the uppermost layer up here, the uppermost layer up here. Once we know the total field specified on that uppermost layer and we solve for the currents, then we can obtain the sheet impedance of that layer. And the trick is to use the known frequency scaling laws for impedances. If I know impedances at one frequency, then I know by frequency scaling for reactances what that impedance is at the next frequency. So we can scale this eta 1, the sheet impedance of this upper layer, the reactances, to the new frequency of F2 using known 1 over j omega c and j omega l. That means we know the sheet impedance on the uppermost layer at frequency 2. And if we know that, and we know the desired total we want at the second frequency, because we know what response we want at both frequencies, I can immediately solve for the current on the uppermost layer at the second frequency, which eliminates one of our unknowns over here in this matrix equation. So we're now solving this one at the new frequency. We can eliminate this as an unknown because we can solve it using the frequency scaling that I just explained. Once we know that, then we can solve each of these equations one at a time instead of simultaneous. So from the first equation of this frequency, remember we know this value. We can now solve for the additional current. We can solve for this unknown because we know this one. And the way we solve that, we end up with an equation that has the total field appearing on the second layer in it. So we've accomplished the goal of finding the total field on that lower layer, which is the difficulty. But now we did that when we had a 0 impedance for the upper layer as a guess. So we'll have to go back in and adjust that in the iterative cycle. So once we have the current on the bottom layer, then we can obtain the impedance because we know the total field up on the bottom layer, and we know the current on the bottom layer now, so we can get the impedance. Then we scale back to the first frequency because this is the impedance at frequency 2 of the bottom layer. We scale back to the first frequency, so now we obtain the bottom layer's impedance at frequency 1, and that's what we originally guessed. So now we have to update that with our calculated value. And we'll update that, and we'll cycle until we get convergence. So that's the big idea there. But that's a breakthrough that allowed us to do dual band metasurfaces. Okay, so that was for 2 metasurfaces. Adding dielectrics and ground plane adds no new unknowns because the impedance of the dielectrics and the ground plane is known. So it's a direct applicable. It's the same exact algorithm that you can apply to a stack like this. So the difference is the integral equation now has five integrals in it, right? So I'll walk you through how these are built up. Same boundary condition. So if we're observing on the uppermost layer only first, then we have the incident field plus is equal to the total field plus the scattered field due to the currents on the metasurface, which are electric surface currents, plus the scattered field due to the volumetric currents in the dielectric, in the first dielectric, plus the scattered field due to the electric surface currents on metasurface 2, the scattered field due to the dielectric, or the polarization currents in the dielectric, in the second dielectric, and then the scattered field due to electric currents on the ground plane. So this one integral equation is for observations made on layer 1. And it's exactly the same as before. We only have this one unknown sheet impedance there, right? Similarly, we can develop another set of 4 integral equations for a total of 5 for observations made in each of the additional layers. So for that integral equation that we constructed for the uppermost layer, we use the method of moment scheme. We expand into pulse basis functions on the surfaces and 2-dimensional or volumetric pulse basis functions for the polarization currents in the dielectric. Use a Galerkin testing scheme, and we can convert that integral equation to a matrix equation like this. Doing the same thing for the additional layers gives you a total of 5 of these matrix equations. We can write these in a block matrix form. And because we know the impedance of the dielectrics, eta V2 and eta V4, as 1 over j omega epsilon naught into epsilon r minus 1 from the volume equivalence principle, we can convert, or these are known values. And we can express the surface impedance of the uppermost layer in terms of the desired total field again, as we did in the 2-layer example. The only unknown will then be eta sheet 3. So we can express this matrix like this, where I've included the primes because these have absorbed the volumetric impedances of the dielectrics. And then I moved the uppermost impedance to the left, like we did before. So the only unknown here is eta sheet 3, which is, now we can use the exact same algorithm to solve that. We guess eta sheet 3 and we iterate around to get the solution. So we're now going to optimize. So if you do that, you'll get a complex sheet impedance. And we need to optimize them using the same approach in order to obtain purely reactive sheets. And the way we'll do that is by the same gradient descent algorithm. The only difference now is the cost function has 2 frequencies in it, 2 responses. We want the desired response of both frequencies. So we have the far, and we're only looking at the far field amplitude now. Previously, we were looking at the near field amplitude and phase, but now we're looking at the far field pattern only. And we have the difference between the complex and reactive sheets for frequency 1, plus the arbitrary difference between the complex and reactive sheets for frequency 2. So here's an example, a dual band metasurface operating at 5.1 gigahertz and at 2.4 gigahertz. And with the original complex sheet impedance for frequency 1, layer 1 is here, and for layer 3, frequency 1 is here. And you can obtain the sheet impedances for frequency 2 by the frequency scaling of these reactances, 1 over j omega c and j omega l for these 2. So I'm only showing the impedances at 1 frequency. Optimizing and obtaining a purely reactive sheet gives you this sheet here for layer 1 and this sheet here for layer 3. And you can see that we've introduced a number of perturbations that will then excite a number of surface waves such that the total field along the surface will give you a reactive sheet, a passive sheet. So this is the response. So the method of moments is the algorithm that we wrote. The complex sheet is blue. So the blue pattern is the complex sheet, the original with the real and imaginary parts. Optimizing out the real part and obtaining a purely reactive sheet is the green. And then I took that optimized reactive sheet and put it into COMSOL and obtained full wave simulations with the FEM solver, which is different than the method of moments, as a verification of my software. And we got the good agreement. So the optimized reactive sheet is working very well at both frequencies. So we wanted to try, we wanted to look at the surface waves. So we look at the total field spectrum again, and we plot the, we want to see how much evanescent content was generated to give us this passive sheet. And it's the same story. We have incident plus the scattered, and we engineered these evanescent surface waves such that when you add them to the incident scattered, you get the total field that gives you local power density conservation. So we can see we generated a lot of surface waves. We need a lot of surface waves and a lot of evanescent contribution in order to achieve a passive metasurface in this case. And you see the blue is the complex, the black is the optimized reactive sheets. So we want to pattern these, but now the patterning has to be dual band patterning. And we just wanted to make sure that the patterning that we designed is, it obeys the same frequency scaling laws that we use in design, 1 over j omega c and j omega l, which is shown here, these black curves, which are underneath these colored curves. So on the vertical axis, we have 5.1 gigahertz. On the horizontal axis, we have 2.4 gigahertz. We have the same library of parts, and we are able to, sweep these parameters L in order to change the reactance. And the one difference here, though, is this parallel resonator element. And the reason we designed that is so that we can get a good short at both frequencies. One branch shorts at one frequency, the other branch shorts at another. But these weren't even necessary at the end. We didn't have any impedances that were close to 0. So patterning this, we have layer 3. So we're looking kind of from underneath the ground plane. We're not showing ground plane or both dielectrics, but we have layer 3 and layer 1. So here's layer 3 and then layer 1. We put it in the same parallel plate waveguide, put PML around it and excited it with the line source. And here we have the ground plane and dielectrics and these pattern layers. So you have all 5 layers and we simulate a full wave and we got these patterns. So the COMSOL pattern is in the black curve on both cases. So this is a pretty good result. It's pretty good agreement, and what this shows is that pattern geometry is able to synthesize that evanescent spectrum, which is here, right? All of this evanescent content that you need exactly these surface waves, exactly these ones, with their exact amplitude and phase, in order to get the passive metasurface. So we were able to get a pretty good, right, using the pattern geometry, which means that our metasurface is designed in such a way that it was homogenizing. Okay. So we did one more example just to show that this can be pushed to a little bit more of an extreme case. We have one beam at 35.75 gigahertz, and we have another beam at 13.4 gigahertz that's scanned off broadside. And using the same exact approach, we have the complex sheet impedance here and here. We optimized out the real part, kept only the reactances, obtained a purely reactive sheet, which gives us the same patterns. And those impedances are shown here and here. And you'll notice the blue line is at 0. And the pattern agreement is excellent. So the complex and the optimized reactive sheets give you the same patterns, but there's a lot of evanescent contribution that the optimized reactive sheet generates in order to obtain that. So now we were getting pretty excited about this work, and we thought maybe we could push it a little bit further. So if I go back, so let me go back. If I go back, what we were doing the whole time was stipulating the phase, and we were solving for the amplitude that we needed that satisfied local power density conservation, or that we thought would, right? So we were stipulating the phase only and solving for the amplitude. But what we want to do now is we want to stipulate the phase and the amplitude. And if we stipulate both the phase and the amplitude, then we're doing arbitrary beamforming with a single pattern metal layer over a dielectric substrate. But so we're asking ourselves, can the surface waves be used to achieve more drastic and arbitrary power density transformations? So now we're going to stipulate, we know that the feed, we're going to stipulate both the amplitude and phase, which means we can do beamforming, we can do arbitrary pattern generation. So what we're going to do is see if that works, right? So we're going to optimize the metasurface to get these surface waves. And for each of the examples I'm about to show you, they are a 16 lambda knot wide. They're on a Rogers 6010 substrate that's 1.27 millimeters thick, and they're all operating at 10 gigahertz. And we only have one frequency here, so there's only one metasurface, and we're doing everything at one frequency, but now we're specifying amplitude and phase. And we have the difference in the complex sheet and the reactive sheet. So as an example, the first example, we have a scanned beam. So we're going to scan the beam 30 degrees off broadside, and we're going to force the side lobe levels to be below minus 20 dB using a Taylor aperture distribution. So this is what we're doing. We have the incident field, amplitude, and phase. That's the phase of the phase and amplitude of the feed is a cylindrical wave, right? We have the blue amplitude and the blue phase. And what we want the metasurface to do is now generate this new amplitude, which has these sort of singularities built up on the end, kind of like a Chevy shed. And we want to change the phase to this, right? So the metasurface that we generate is gonna change this blue phase and amplitude into the red phase and amplitude upon reflection. What we have here is the complex sheet. So we find the complex sheet first because we need that in order to seed our optimizer and also build our cost function around. We find the complex sheet here, has real parts, and then we optimized out the real part and obtained a purely reactive sheet with these perturbations that will give us this field transformation. And one interesting thing about this, if you look at the power density, normal component power density, remember before we wanted the scattered and incident to be equal to each other, with the negatives up, right? But here, we're now allowing those to be different. So the metasurface is transforming power density profiles. So the blue is the complex sheet power density profile, and the red is the optimized reactive. So we're actually changing this black curve. We're building up to singularity, just shoveling power around on the surface now. So this is the result. We had a complex and optimized reactive sheet. And we back projected these far fields to the near field, to the metasurface plane, to see if we were also shaping the near field. And we were. So we have the optimized near field amplitude and near field phase, complex and optimized reactive sheets. So we're building the cost function around the far field amplitude only, which allows us to do the optimization a bit easier. But that's also inherently shaping the near field amplitude and phase as well. And if we look at the spectrum, same as we've been doing, we see that the complex sheet has very little evanescent contribution and no surface waves. And then the optimized reactive sheet has a lot of evanescent contribution or evanescent content, and that content generates the surface waves that we need in order to achieve this transformation. If we zoom into the visible region only, so now I'm plotting down here -1 to +1 k naught, or -1 to +1 k naught, you see that we get the same radiative near field and therefore far field, but we have different invisible spectrum or evanescent fields. So as a second example, we wanted to take a cylindrical wave and transform it into two beams. One beam goes off to 30 degrees off broadside, the other goes to 40 degrees off broadside, and both beams have -30 dB side lobe levels. So what we have here is the cylindrical wave in blue, amplitude and phase, and we want to use the metasurface to transform that cylindrical wave into this amplitude and phase, which has sort of the interference pattern between the two beams and sort of this phase distribution that's got this kind of rectangular wave with a slant to it. So that's a pretty dramatic transformation. This smooth blue curve into this red choppy curve using the surface waves. All the surface waves have to interfere and add up in order to generate this kind of result. So here's the complex metasurface, and here's the optimized reactive metasurface that we got, purely reactive. And here's the results. Complex beam and optimized reactive beam, they both agree very well. Back project those beams back to the near field, and we got the desired response, the amplitude and phase and the aperture using the surface waves. And if we look at the spectrum again, we have all this evanescent content, which is generated by the optimized reactive sheet in order to allow us to do this transformation, which is a completely arbitrarily specified amplitude and phase, meaning we can do beamforming with just a pattern surface, which is, remember before at the beginning of the presentation, I showed you have to use multi-layer PCBs with ICs. In the case of a phase array, you have to shape a reflector, or you'd have to use multiple layers of a metasurface or those kind of technologies to get this kind of response. But now we can specify arbitrarily amplitude and phase of the far field pattern and also the near fields, and just pattern a surface, pattern a substrate, and we can get whatever beams we want out of it, really. And so the near fields are also, the visible region spectrum is also correct. So we kept feeding this thing with a source above the metasurface, which has like volumetric requirements, right? So metasurface antenna designs, we want to kind of make everything compact. So this is another example where we now bring the feed into the substrate. So we put the pin in the substrate, and it's an infinite line source in and out of the board. And this thing will launch a certain incident field, which will interact with the metasurface, and that will generate some kind of desired field. So what we're doing here now is a compact metasurface antenna, and has no volumetric requirements outside of the metasurface substrate. And we want to make this cylindrical line source here convert into a perfect aperture, which is uniform amplitude and phase. So here is the blue curve of the incident field amplitude, the blue curve of the incident field phase. We want to transform that with the metasurface into a scattered field amplitude and phase, which is uniform, which is indicative of perfect taper efficiency. So that's what we're trying to do here. So this side lobe envelope will be our sinc function with -13.4 dB side lobes, and we'll have that 1/x decay, indicative of a sinc function. So here's a complex metasurface sheet impedances. So one thing I might have left out is that when you design the complex metasurface, the one thing, so we specify this scattered field amplitude, right? But the scattered field amplitude, you know the distribution because it's related to the beam, but what is the absolute level? You know, this is 2,900 volts per meter. How do we find that? Well, we match global power. So if you integrate the power, the global power, if you integrate the power density along the surface of this incident field, you'll have some number. If you integrate the power of your scattered field along the surface, the power density, you'll get the global power of the scattered field. Those two have to be equal. Because if you want it to be passive at the end, then you want to have a global power conservation. So that's how we find the amplitude here. But the distribution is, of course, related to the beam. So we get this purely reactive metasurface there. So here are the results. These are still underway, right? They're still converging a little, but we're nearly there. So this one we have a broadside beam, and we have 13.4 dB silos. Complex and optimized reactive sheet are agreeing pretty well. If you back project this back to near field, we're almost there in near field amplitude and phase. If you look at the spectrum, we're almost synthesizing the total spectrum. So it's still running, but it's nearly there. So one thing that's interesting to notice with this pin in the substrate is that the evanescent contribution to the complex sheet is all. We have a lot of evanescent content in the complex sheet. That pin in the substrate generates a lot of evanescence content by itself in the incident field, and the complex sheet therefore has some of this. So we're basically reshaping what we have there already. But this is looking very good. So now we want to move to three-dimensional. Everything we did before was two-dimensional metasurfaces. We want to move to three-dimensional metasurfaces that are practical. And we also want to look at doing conformal metasurfaces. So the idea here is to combine all those topics that we had just discussed. We have an incident field, maybe a cosine Q, coming in at both frequency F1 and F2 on a conformal metasurface and multi-layered, and get dual band responses out of it from conformal surfaces in 3D. So maybe at F1, we reflect it off in this direction. We have this sort of beam with arbitrarily defined amplitude and phase. So it's beamforming with passive metasurfaces at 2 frequencies, or you could add additional frequencies, more layers, and from conformal metasurfaces that are 3-dimensional. And then maybe this frequency scans off to that direction. So now what we have is sort of a conformal metasurface. You have 2 metasurfaces, 2 dielectrics, and a ground plane still. And these are separated by some distance d1 and d2. Here's the integral equation that we need to solve now to design conformal 3-dimensional metasurfaces. This is the well-known integral equation for using the RWG basis functions, or triangular basis functions. So you might be able to triangular facet one of these metasurfaces like this, and then construct an integral equation around it. And we have basically the voltage vector here. We have the total field matrix that we had before, for the eta sheet times the current density. So you'll recognize this as the expansion for the current density. Then you'll recognize this as our eta sheet, which is now a surface impedance tensor. It has both polarizations in it, X and Y. And then we have the inner product with the testing function, which is also a RWG basis. And then we have the current density, the current coefficients here, and the coupling matrix, or the impedance matrix from there. So using this, we were able to design this metasurface. So we have a x-polarized point source, which is a cosine Q function or cosine Q pattern with a Q factor of 0 at 10 gigahertz, exciting a conformal metasurface here. And this conformal metasurface is 6 lambda long and 1 lambda wide. And if this was PEC, if this conformal metasurface was made with perfect electric conducting material, then this point source would generate this red pattern upon reflection. So you can see we get a null at 0, and it throws a lot of the energy off in this direction because it's the broadest side. If you use our approach to design the metasurface, then if this becomes a metasurface and not PEC defined by some impedance tensor, then you can get a collimated beam like this blue beam, for example. So this one I designed by saying, well, I want that metasurface to generate a plane wave or a collimated beam back toward the source. And this is pretty cool. Coming from a conformal surface that's 3-dimensional, we can design metasurfaces to give us arbitrary beamforming again from conformal surface. So arbitrary surfaces, arbitrarily defined frequencies of separation, and arbitrarily defined patterns or responses that we want from it. So it's the most general thing. So if we look at the metasurface impedance matrix, we know that, so these elements are assumed to not couple X and Y polarizations the way you would design the geometries. So we have the real part of ZX and the imaginary part of ZX, the real part of ZY, imaginary part of ZY. So this is like copole and crosspole, if you will. And each of these, I'm looking at them from directly above. So they're really curved surfaces like this. But if you look at it from directly above, it would look like this. So this is the impedance that is required. But notice that these are complex. So what we're doing now is we're using our same optimization codes to generate purely reactive sheets on conformal or arbitrarily defined surfaces, arbitrarily defined beams, at arbitrarily defined frequencies. Normally when you design like a reflector array, for example, you have to pick your frequencies of separation F1, F2, such that you can design elements where they don't interfere with each other. Because normally you want to tune the response at one frequency without having to worry about the effect on the other frequency. So the other frequencies are operating as background. And then you go back to this frequency and you tune this one independently and won't affect the original. But now, since we're designing both frequencies simultaneously with our iterative algorithm, we can define any frequency of separation. So arbitrary frequencies of separation, arbitrary number of frequencies, arbitrary surfaces, arbitrary beams, which is basically everything we want. And that's the result that we got there. So we're still working on that kind of thing. So in conclusion, the main theme of this talk was that we want to engineer a number of surface waves such that we can add to an arbitrarily defined scattered field and a known incident field to generate a total field that satisfies local power density conservation and gives us a passive metasurface, which can be patterned purely reactive elements and arbitrary beamforming with. So I can get a substrate from Rogers and I can just etch it with a pattern that I engineer, and I can get arbitrary beamforming out of it, which is much different than a phased array. I have to put ICs on the back, have excitation coefficients, amplitude and phase for every element, or I have to shape some reflector and get it manufactured. Difficult to do that, to manufacture a shape reflector, or multiple layers of metasurfaces. This is very interesting. And another thing we were able to do with that is to get a metasurface antenna with a pin in the substrate, make all the volumetric requirements, go down to 0. And then we have 3D conformal metasurfaces that we're also able to design with this, which is our work that we're leading into with all of this. And these are the references for the presented work in my email at the bottom. And with that, I would like to thank you for your attention and open up the floor to questions.
Wonderful. Thank you so much, Jordan. So virtual round of applause for Jordan. I know we can't clap out loud, but I hope you hear a whole bunch of people clapping for you. That's wonderful. Welcome people to put questions in the Q&A. I've also now given you permission to unmute yourself. So if anyone wants to speak up, feel free to just unmute yourself and speak, or to put your question or even just your name in the chat and I can call on you. So while we're waiting for people to type in the chat, let me just ask you sort of high-level question about this. And this is sort of these antennas. What are the particular application spaces that you're looking to deploy these antennas in?
Well, you can think of a couple applications, like some space applications where you could have dual band performance, where a lot of times when you build antennas for like CubeSats and things like that, you need very low profile, small volumetric requirements on those, size, weight, and power. So that's one application. Another thing is electromagnetic illusions or carpet cloaks, where you might have like a surface that you're trying to hide or have anomalous reflection from, like maybe a cylinder, right? And if I have a conformal metasurface, so it has to be conformal, and I have to pattern it to be reactive. So when the light reflects off of that cylindrical surface, that it gives you an anomalous reflection that might look like a wall behind it, so that that requires conformal metasurfaces, and maybe even 3 bands, right? We need our red, green, and blue. So this work is multi-band conformal metasurfaces that will lead directly into that kind of work.
Excellent, great. And can you compare the benefits of your metasurface antennas compared with conventional antennas that already exist or that are in development? What are the advantages of metasurfaces that we should be aware of?
The advantage of metasurfaces is simplicity, right? We're just patterning a substrate that we get from Rogers, and we can get arbitrary beam forming out of it, right? Otherwise, we'd have to use a bunch of ICs, vias, multiple layers, or shaping and difficult manufacturing techniques. So that's one advantage. Another advantage is we can do extreme wavefront control, right? We can put the pin down in the substrate and get rid of the volumetric requirements. There's the benefits in that area as well. And of course, since these are planar or very thin, right? Not necessarily planar, but very thin, then we can also make conformal metasurfaces that can be wrapped around, military vehicles or anything to require stealth or illusions or whatever have you. So there's that, a simplicity and extreme wavefront engineering.
Great. Looks like we have a question in the chat from Zachary Fritz. Zachary, do you want to unmute yourself and speak, or shall I read your question? give him a second, see if he wants to unmute. Okay, let me read out his question, then he can join and follow up. So he wrote, thank you for the well-explained presentation. Jordan, for the dual band metasurface design process, is the convergence of the iterative process for finding the sheet impedances guaranteed if certain conditions are met? He said, I believe the relevant slide is 21.
21, okay. I can go back up to 21, but I think I understand this question. So is the convergence guaranteed? If you include the real part and the imaginary part when you first design the metasurface, then you will get a design, right? If you have control over the amplitude and phase with real and imaginary parts. When you optimize out the real part and you end up with a purely reactive sheet, the convergence, I can't comment on whether it's guaranteed, right? Every example that I've optimized is possible. You might need a finer discretization and allow certain evanescent content to be generated. But in terms of a mathematical proof or a way that I can speak confidently that it's guaranteed, that would require some more investigation into that. Yeah, that's how I would answer that.
Okay, great. Let's see, we have another question that popped up in the chat here. This is from Weihui Gu. He says, hi, Jordan, an impressive work. I have a question on the MOM formulation for solving this problem. Can you explain what Green's function you are using and how you consider the interactions between different layers?
Excellent. Okay. The Green's function that we're using is the free space Green's function. So every current that we're modeling is, we use surface equivalence theorem or volume equivalence theorem to have those currents then rated in free space. And therefore, we can use a free space Green's function. The way we're modeling the coupling between the different layers is through the coupling matrix, right? We wrote an integral equation for each layer, and we solved all of those integral equations simultaneously in matrix form. So we had a sort of a block matrix with all of the integral equations that coupled all the currents to each of the layers. So Green's function is free space based on equivalence theorems. And the coupling is by solving, a system of integral equations simultaneously in matrix form.
Great. Okay. Another follow-up question from Michael Kirkhart. He asked, have you constructed any of these metasurface antennas? If so, how well did the experimental performance match up with the simulations?
Excellent question. Yeah, we're in the process of getting some of those fabricated now. We haven't built any yet, but we will be building those. We have full wave simulations, so we're expecting at least to agree with our full wave simulations. But we have plans to fabricate some of these. And when we get to like the 3D conformal, for example, we would have 3D printed conformal dielectrics. We're looking into methods to 3D print sort of conformal substrates and then electroplate and etch those. So yeah, we have full wave simulation results, but soon we'll have measure results. So I guess you could keep an eye out for papers on that.
Great, wonderful. I had another question as well, and I was just wondering, you nicely showed how this could scale up to at least 2 frequencies. Is there any limit on the number of bands that you could use in scaling up this technology? Where are the limits of this multi-band metasurface antenna approach?
Yeah, I think at some point it might get a bit thick, right? I mean, theoretically, you can add more. Each additional layer could give you the degrees of freedom for another frequency. So maybe 3 layers for a 3-band or tri-band metasurface. But if you have very far separated frequencies, then you might have trouble discretizing it, right? So you have to homogenize. You have to discretize it at the highest frequency such that it's homogenizable. And then if you have a frequency way up here, right, and you have an element which gives you sort of a homogenized response, but you have a very low frequency, then within the real estate, so that same pattern element has to respond at both those frequencies. Within the real estate of your element at the higher frequency, at the lower frequency, it'll be even smaller, yeah? So it'll be, you might not have enough room to get the inductance and things. So there's realizability, you might have some things to think about there. But yeah, you could definitely do multiple bands. You just have to make sure you can pattern.
Great. Okay. One other question that came in here, again from Michael Kirkhart. He asked, when you ran the simulations, did you generate the S11 plots, the reflectance plots?
The S11 plots. Okay, when I ran the simulations. So what I was looking at in simulation, so I didn't excite it with a port per se when I ran the full wave simulations. What I had was an infinite line source. I just imposed a current that was associated with an infinite line source and had that scatter. So it's a scattering problem. And then I calculated the currents on the bounding box and then did the FFT to get the far fields. So I was looking more at scattering in far fields instead of, you know, I didn't excite it with a waveport. So I excited it more with a line source.
I see. Okay, yeah. He further was specifying in the chat that he was talking about the feed point impedance and whether you had looked at how that's affected by the creation of this metasurface antenna.
I see. Yeah. So in the case where the feed is much higher than the metasurface, I wouldn't expect that coupling would throw off the impedance. And again, we were just looking at, you know, a line source, a driven line source current. But in the case where the feed is in the metasurface, you might have to pay attention to that. So I think that's maybe where he's going with that. You might have, there's a lot of coupling going on there, so you might have to design the feed, you know, in order to, which might be a difficult thing, right? Then you have to include the feed in the optimization. So you have to optimize the metasurface and the feed to make sure you still match. And somewhere at the end, you're gonna have to drive it anyway. So with a 50 ohm source. So yeah, he's right. You need to include that when you get to sort of the one where the pin is in the substrate. But when you're feeding it from outside, like if you feed a reflector with a horn, then a lot of times you can design the horn, you know, independently in terms of its input impedance match.
Great. Okay. Just don't see any more questions in the chat. I'll just close with one final question. Is that you've hinted at this in several of your answers so far, but can you give the audience sort of a feel? What are the key challenges in metasurface antennas that you're trying to attack right now, or that others in the field are trying to attack? Where should we look for new work to be coming out in the next year or two in this area?
Yeah, sure. So first off, the way we are designing these metasurfaces. So, you know, previously you designed metasurfaces with some, you know, canonical formulas that are for infinite sheets or whatever have you, that are infinitely thin. So they're all designing them with boundaries, which are called the GSTC, generalized sheet transition condition. We are modeling the actual thickness of the metasurface by using our integral equations. We are making it very practical. We are modeling the coupling between the ground plane and the finite width of the metasurface as well. And so that's one key challenge, you know, making practical metasurfaces that you can realize and get good results with. That's one thing. And the other thing is conformal metasurfaces as kind of a new thing. It's kind of a topic that might have a lot of new researchers entering the field doing that as well. And then the purely reactive metasurface. A lot of times you can do these transformations, you might end up with a real part and imaginary part a lot of times, right? So trying to find a way to get purely reactive metasurface, the theme of my work, is another contribution that might be so, and multiband as well. All of these things are things that we kind of pioneered over the last few years.
Excellent. Great. Well, thank you so much for sharing your expertise with us. I think it's been a really insightful talk and helped open all of our eyes to the great work that is going on in Michigan in this area. So thank you so much, Jordan, for taking the time to talk with us today.
All right. Thank you very much.
Great. And thanks to all of our audience for joining us today as well. I hope you benefited, and to everybody, a very happy holidays and happy new year in 2021. Take care.
All right.